Hello everyone and welcome in this low frequency session. I am Spiros Malios, a business development manager in digital twin technology, and today we're going to focus in AI power engineering and more specifically our reduced order modeling and system identification software ROMAI. So, before we dive into, let's see a little bit about where artificial intelligence can be applied in engineering applications. On the left side, we have the component level analysis, where we want to basically optimize the design and the structure of a part. And on the right hand side, we have the system level analysis, where we can basically want to see how well an individual system is operating and integrating with the rest of the other systems. So we want to perform some systems of systems simulations. Now, artificial intelligence can be applied in both of these domains, and Altair has a solution for both of these scenarios. Now, on the left side, we have our geometric deep learning engine software, which is called Physics AI. We are going to dive into this software more into detail on another session later. And on this session, we are going to cover mostly our reduced order modeling and dynamic and system identification software, ROMAI, which relies on the deep learning and dynamic system theory combination of technologies. So we see that in the industry more and more people are talking about digital twins, and of course digital twin is a digital representation of your physical asset, your physical product, and a big challenge is to create efficient and accurate digital twins. And we see that more and more there is the need to be able to efficiently integrate data coming from the simulation world, so CAE data, and data coming from the field, so from real world measurements. And you need to be able to integrate those two in order to create an efficient digital twin model. And this is what we call basically a hybrid digital twin. Now, let me introduce you to our digital twin platform and systems integration platform, which is Altair Twin Activate, where we can basically create models using a variety of different modeling languages, so from script to block, and also integrate these modeling languages with native 3D solvers, CAE solvers, or third-party solvers via the FMI standard. Now, this means that we have a very flexible platform in terms of what kind of fidelity you want to choose, ranging from 0D all the way to 3D. And on top of that, we have an optimization, built-in optimization capabilities. And last but not least, what we're going to cover mostly today is our ability to create models based on artificial intelligence, reduced order models, with ROMAI. ROMAI lives inside Twin Activate, but most important is that this platform also allows you to create true digital twins, meaning that these models can communicate with the outside world via the most common communication platforms, communication protocols, So, what do we mean with the term dynamic system modeling? Here we have, let's say, an analogy of a guitar system and a tuner. Basically, artificial intelligence is acting as the tuner and helping you tune your model to match the actual physical asset or your high fidelity 3D simulation. So AI is helping you create a dynamic system model basically by tuning the system equations for you. What our software is actually helping you do, identify your system properly. And how is ROMAI different, let's say, compared to the competition? So under the hood, we have a very unique combination of deep learning and dynamic system theory. That means that we can create very efficient nonlinear dynamic reduced order models that are able to generalize well and be used outside of the training range in a lot of scenarios. Now, what is required to build these reduced order models? So, of course, you need some data, so you can have a data set that can be from either simulation or test data. Now, it's important to note here that this data doesn't have to be on a fixed time interval. It can come into a variable, from a variable time step. And of course, what is also required is from the user to identify what would be the inputs, the outputs, and in case of a dynamic system, what would be the states. Now, the states are basically representing what is the memory in the system. Now, what the software is going to do for you is, based on this information, it's going to build a dynamic model, a dynamic reduced order model that you can later use for your application. Now, it's important to note that ROMAI is a no-code application. There is no scripting, no coding required whatsoever. So as we said before, data can come from simulation or real-world test, from test benches, and you can actually build static or dynamic models, meaning that with a static model, basically there is a fixed relationship between the input and the output, whereas on dynamic models, you can model also the transient response, so model any dynamics, any vibrations or oscillations in your system. Now, what is nice with ROMAI is that it's virtually, we can integrate the ROMAI model into any application, so it can be integrated. Sorry, I'm going to take this from before. So what is nice with ROMAI is that our ability to deploy it in virtually anywhere. So we can deploy it in the software, in hardware, and the cloud. And that means that, for example, you can use it into hardware in the loop application. You can embed it into actual hardware, into controllers running parallel with your physical asset. Or, of course, you can integrate it into your favorite software to perform an optimization or a larger system of system simulation. Now, there are two flavors when using ROMAI. You can either create some reduced order models, and when we deal with reduced order models, basically data is coming through simulations, so through the CA world. And what is the benefit of a reduced order model? Of course, this reduced order model is running much faster than the original simulation, so you can use it for optimization purposes, but most often you can use it to perform some larger system of system simulations. So if you take, for example, this wheel loader on the bottom left of your screen, there was the bottleneck of the particle simulation here, and the reduced order model was identified in order to speed up this co-simulation here of the multi-body solver and the particle solver, the discrete element solver. So with this integration, you can basically expect some reduce in the overall co-simulation time with this technology. Now, on the other hand side, we have the system identification world, where you basically work with data coming through tests. That means that you basically perform some tests in your lab, in your environment, and you treat this data, you use it inside ROMAI to basically identify a dynamic model, a dynamic reduced order model, which can later be used into larger system of system simulations again. Basically, the scenario here is that it's very often that you cannot simulate very complex systems, so you need to actually perform some real-world measurements, some real-world data, but then you want to actually perform the overall system simulation. So basically, ROMAI is going to help you here identify this very difficult to model system and integrate it with the rest of your systems. Now it's on the right-hand side here, you see an application, for example, on some battery cells, and it's important to note here that this is a dynamic model, and you can see that we capture also the hysteresis effects in various different temperatures. Now, I would like to thank you for joining us here. This was again an intro on this technology. Stay tuned for some induction machine relevant applications using this technology, and we are looking forward to hearing your challenges and working with you. Thank you.